So, titration, substance changes into a new substance when its properties change, no mass is gained or lost. That's conservation of mass. And what we're going to see here. In this particular section, define terms that describe the parts of a titration. These are the terms we'll be defining: analyte, titrant, equivalence point, and endpoint. Then we're going to calculate using stoichiometry to figure out our unknowns, our analytes, and our titrations. Okay, so what is a titration? A titration is an analytical lab technique where a known volume and molarity of a titrant is dispensed from a burette into a flask containing a measured volume of an analyte. And the way the burettes look, they're long glass-like structures that are held up here by a burette clamp. Okay, the burette clamp holds it to the ring stand. And it has a valve here. So you turn the valve and the solution will flow out of the burette into the flask. Now you can manipulate the valve so it has a faster flow, or you can manipulate the valve so it like drips. So it has a little drop-wise fashion. And you'll see this setup in the Pivot Interactives lab that you'll be doing. It'll be like this in the burette. Now the lab that we're going to do the following class with the permanganate, the redox titration lab that we're going to do, we have micro scaled it. So instead of burettes, you'll be using syringes that are pretty small. We'll be using less chemical, but it's the same idea. You'll still be adding it and figuring out the unknown concentration. The one that's in the burette, the titrant, that's the one that you know about. The one that's in the flask, the only thing you know about it is that how much volume you put in there. So, standardized solution is also a name we call the titrant. It's the one that we know the molarity of. Okay? And yes, notice that the word burette is spelled two different ways in different places. So if you're looking at stuff on the internet or in other textbooks, you might see it written either way. The analyte is the one that you don't know the molarity of, or you're trying to confirm the molarity of. And usually, because we're dealing with solutions most of the time, you're going to measure a certain volume of that unknown and put it into the flask. Now, by using a balanced chemical equation specific to the reaction, moles of the titrant can be determined at the equivalence point. I'm going to show you how to calculate that. The equivalence point is when the moles of the titrant and the moles of the analyte are stoichiometrically equivalent. So use the mole ratio in the balanced equation, you'll be able to get to that equivalence point. This means the moles of the titrant react with the moles of the analyte in a mole ratio determined by the balanced equation. And in order to know when this point has been reached, this equivalence point, the stoichiometric, where the moles are balanced with the other moles, usually there's an indicator in the flask that's going to change colors. And when the color changes, you know to stop the titration, and when the color changes, it's called the end point. So as you can see in this picture over here, it started off analyte, like clear like the blue, like the flask color here, but when it got to its final reading, or got to the equivalence point here, it ended up being that purple color, so it changed color. So, equivalence point versus endpoint. They are two separate definitions, and you need to make sure that you understand that. Equivalence point is when enough titrant has been added to react exactly with the substance in solution being titrated by the mole ratio in the balanced equation. So stoichiometric mole ratio point is the equivalence point. The end point is when the indicator changes color.
When the indicator starts changing color, or once it has completely changed color?
It's usually right when it starts changing, and that particular color persists.
Okay.
So you don't need to go super dark, you just need to have that color persist a little bit.
Okay, thank you.
Now, the equivalence point is not necessarily the same as the end point, but ideally, you're going to pick an indicator that will change color at your equivalence point. You won't pick an indicator if you're trying to do a reaction where you know the equivalence point is going to be at a pH of 7. You're not going to pick an indicator that changes color at pH of 3, because that would be silly. You're going to pick one that changes color at pH of 7, so that you know when to stop your titration. Okay? Acid-base titrations. So acid-base titrations, either the acid or the base can be the titrant or the analyte. So the titrant usually is the one that goes in the burette. The analyte is usually the one that goes in the flask. Sometimes they switch them, but for the most part, that's the normal way of doing it. An acid-base indicator, which changes at a color pH close to 7, is added to determine the endpoint of a strong acid-base reaction. That is because a strong acid being titrated by a strong base, or vice versa, the pH is always going to, the equivalence point is always going to be at a pH of 7. And later on, you'll find out why when we get to the acid-base unit. Sometimes pH meters or probes are used to determine the equivalence point. And we do have pH probes that go with our Logger Pro system. So when we get to acids and bases, we'll be doing a titration there and be using it to create the titration curve. Now, what data should be recorded if you're doing a titration? We need to record the volume and or mass of the analyte. So whatever you're taking out of the original analyte to put in the flask, you measure out that volume or mass. The molarity of the titrant, you need to have that recorded because that's the one that you know what its concentration is. And the initial volume of the titrant. So initial volume be somewhere up here at the top of the burette. Now what you should also know about burettes is they have a reverse scale. So like 0 is all the way up here, and then they usually go to like 50 milliliters down here. So you kind of have to read it upside down. It's inverted. So you still read it from the bottom of the meniscus, but you read it backwards. Okay? So initial reading at the top. Then you also need the final reading wherever it stopped, because once you have the initial and final, you can do the subtraction to figure out how much volume was actually added. And once you have that value, you can, excuse me, we'll go back. Once you have that value, this volume of your titrant, okay, and you know the molarity of your titrant, so that means from the molarity equation, you should be able to find the moles of your titrant. Because if you know how much was added, and you know its molarity, you can find the moles, use the mole ratio, now you can find moles of analyte. And don't worry, we're going to work some problems with this. Lots of problems. Acid-base indicators, though, before we get into problems. They change colors at different pH values. For example, phenolphthalein. And this is the indicator they use in the pivot lab. So you'll see this one changing colors. There are two basic colors to phenolphthalein. You have the pink color, that's like hot pink, and then you have clear. And it changes around a pH of 8. Like 8 to 9 in there is when the phenolphthalein changes color. And we use phenolphthalein quite often in titrations. What you'll notice too about indicators, if you ever look them up, is they are big organic molecules. This is the colorless form right here. You have 3 benzene rings, 1, 2, 3 in it. It's a big organic molecule. The pink form, you can see over here is where the change occurred. They took off an H, okay, double bonded an O, and now it has a slightly different configuration, so it turns into the pink color. But indicators are usually big organic molecules. A couple others that we use a lot of times is bromothymol blue and universal indicator. Now bromothymol blue is especially good for strong because as you can see, it changes color right around pH of 7. pH of 7, here, you can see it's turning green just slightly for a moment before it goes to blue. Now, universal indicator is one you're probably familiar with because that's the one that they make the pH paper out of. But we also have solution form of universal indicator, and it still does all the colors of the rainbow. We'll be using that indicator later on in the year for one of the electrolysis labs because it does all the rainbow colors pretty good. So we'll be using indicators like these. Now, I pointed out to you 3 indicators that you'll see throughout the year, but realize there are lots of indicators. This is just one chart that has many on it, and as you can see, they change colors at different pHs. So, if you know your equivalence point is going to be like around 3 or 4, 3 or 4 here, you would want to be looking at something that's going to change color. No, that's 2 or 3, sorry. 3 or 4, you would probably want to stick with something like in here, because those ones will change color around the 3 or 4 range. If you're looking for an equivalence point that's higher, somewhere in the 10, okay, you probably want to stick with this one. It's changing colors into the purple blue thing. That one is thymolphthalein. You can see here bromothymol blue right here in the middle for 7. Okay, the phenol red's a good one for right around 7 for the strongs. And we do have phenol red back there, we just don't use it all that often. And as I said, you can see the universal indicator goes across the entire rainbow. But there are many indicators out there that can be used in acid-base titrations. Now, titration curves. And like I said, we will be doing a full-out titration where we're going to create the curve and all of that later on in the year. But basically what you see here, it looks like an S-shaped graph. The S-shaped graph is created from a plot of the pH of the analyte. The pH goes on the Y. Okay? And the amount of the titrant added goes across here on the X. So the standardized solution, don't forget that's just another word for titrant. So that's what you're plotting across the X, is how much of the titrant you're adding. So for example, this could be a titration of a strong acid like hydrochloric acid with standardized sodium hydroxide. Standardized sodium hydroxide means we know the concentration of it. And you slowly add it, and you record the pH as you slowly add it. Then it turns into this weird S-shaped curve with this vertical inflection point in the middle. That vertical inflection point is telling you where the equivalence point is. So that's going to be the volume at the equivalence point when it starts to do the inflection. And as you'll notice, the inflection point's right here in the middle at pH of 7. Okay? Because this is a strong acid, strong base titration. pH at the equivalence point for a strong acid base titration is 7. Now when we get into the weak acid base stuff later on in Unit 8, you'll see that some of them are not going to be at 7 exactly. But strong, always going to be 7. Did want to show you that the previous graph was a strong acid being titrated by a strong base. So you start lower in the pHs, get to the inflection point, you add a little bit more base at the end, you get the higher pHs. If you're titrating a strong base with a strong acid, you're going to have the reverse. It's still going to be like the S-shaped curve, but you start at the higher pHs because you're adding the acid. You do get to the equivalence point where you have that inflection, like you have that vertical drop. And then over to the right, you'll see after you've added more acid, the pHs remain low. So it's really the same kind of idea, except for the S is flipped, because you start at higher pHs if you're titrating a base with a strong acid. Neutralization of a strong acid by a strong base. The net ionic equation for strong is always going to be H plus OH minus gives you water. Now let's think about this. As our other example here, hydrochloric acid, sodium hydroxide, that gives us water, and sodium chloride. If you think about this, strong acids, completely ionized. So these are going to break apart. These are going to break apart into ions. Sodium chloride is soluble, so that's going to break apart into ions as well, right? So we're going to end up having both sodium and chloride spectating. They're both spectators. So spectators we remove out of the equation. So the only thing left that's actually reacting is the hydrogen plus the hydroxide giving you water. Now there's a nice little animation here. I'm going to show you, talk you through it, so you can kind of see the interaction of what's going on in a neutralization. Okay, so let's take a look at this animation here. All right, so there's the burette with the valve, looking at it on the molecular level. As you can see, they remove the water molecules. Now, over here is our key. You can see regular water is just the grayed out ones here. The one outlined in blue, that's hydronium, because there's 3 hydrogens in the 1 oxygen, and it has the plus, so that's hydronium. Chloride and sodium. So basically this is, we're starting with hydrochloric acid here, right? We have 1 hydronium, we have 1 chloride in here. You can see the water is facing the correct direction towards the chloride because the hydrogens would face in. Now, you can see the pH is about 4, so it's not very concentrated, but it is acidic, because below 7 would be acidic. Now we're going to add the sodium hydroxide, and it's going to kind of give you an idea too of how the H actually interacts with the water molecules. So pay attention. The H detaches and reattaches a lot. So here it's going to detach, and now it's going to be on that water, and now it's going to be on that water, and so forth. So the H kind of just hops around from water molecule to water molecule. Now we add in some hydroxide. So as you can see, the hydroxide will do the same. Pass the H along. There, the hydronium combines with the hydroxide, and now it's neutralized. But now, this is like the other end of the titration. The pH was going up, so it's like this is now we're above the inflection point because we've added in excess of the sodium hydroxide. So you saw the pH go up, and we're past the equivalence point for the titration. Okay? And they add the waters back in. Okay, so that's a good little scale, gives you some more particulate model diagram idea. So now we're about to get into the calculations, titration calculations. First and foremost, you need to write out a balanced equation if one is not already there. Find the volume of the titrant and convert it to liters. Find the moles of the titrant using the known molarity and the liters from number 2. So this one you're working off of the molarity equation, right? If you know the liters, you know the molarity, you can find the moles. Then you're going to find the moles of the analyte using the mole ratio. This is the stoichiometry part of the deal. And then if you divide the moles of the analyte by its original liters of solution, you can figure out its concentration or its molarity. So, this one is a nice big word problem with a titration. Take a moment to read through it. Okay, so first things first, what should we do?
Write the balance equation.
Write the equation. So what's reacting here? HCl plus NaOH. So, acid plus base always gives you water and the salt. So the salt here is going to be the combination of the sodium and the chloride together. So that's going to make our salt. Now, do we need any coefficients for balancing here? No, this one does balance out. Everything in it is 1 to 1 to 1 to 1 for the mole ratio. So we're good with that. Now, next step is to find what?
Volume of the
Volume of the titrant. Which one is our titrant here? Which one do we know the concentration of? NaOH. So this one is our titrant. Okay? And it tells us that the initial volume was 0.51 milliliters and the final volume was 18.50 milliliters. So here we go with step 2. 18.50 milliliters minus 0.51 milliliters. So that gives us 17.99 milliliters that was added to the flask. What do we still need to do with that? Change it to liters. Okay. 1, 2, 3. Okay, so 0.01799 liters. All right, now, next step is to find the moles of your titrant. And you can combine it with finding the moles of the analyte because it goes nicely in one big dimensional analysis T-chart. So I'm going to do 3 and 4 together here. So we start with our liters of our titrant. I can use the molarity of the titrant, which happens to be 0.4 molar here, as a conversion factor. And then I can go right into the mole ratio. So 1 mole of the sodium hydroxide is equivalent to 1 mole of the HCl. And now I'm getting the moles of our analyte in one T-chart. So I don't have to stop and individually find the moles of the sodium hydroxide. I can just go, if I do it this way, it takes less time. Now you're welcome to use the molarity equation, find the moles of the NaOH, and then do the 1-to-1. Like I said, piecemealing it together just makes it take longer. So here we go, we get our moles, 0.007196, and I would wait to round this till the end. This is the moles of the HCl. So in order to find concentration though, we need to use the molarity equation, right? And what are we going to divide this by? the liters of the original amount that was put in the flask, which is 10 milliliters were put in there. It really doesn't matter if you add water afterwards, because the titration itself is really getting you to the equivalence point, which is moles being equivalent to moles. But the original amount that was dispensed in there is the volume that I need to determine my concentration from. So I changed that one to liters. 1, 2, 3. Right, now I can divide that over here. Fix that. Liters. Okay, and now we get our final concentration. And since here this has 3 significant figures, I'm going to keep it at 3. So 0.0, no, don't need a 0, those go away. This is 0.720 molar HCl. If you round it to 3 significant figures, due to that molarity being 3 significant figures. So this is the first version of a titration. Basically what you're going to do in the lab on Friday. And you're also going to, no, this one actually is going to be very similar to the pivot lab that you're going to be doing online. The one in the lab is going to be a redox one. The one on the pivot is acid base. So keep that in mind. Now you could have a problem like this, where they give you a titration curve. 20 milliliters of hydrochloric acid with an unknown concentration is titrated with 0.450 molar sodium hydroxide. Find the molarity based on the data provided. What do I know that my titration curve can tell me about the titration?
The equivalence point?
The equivalence point. The equivalence point is 7, but why is that important? Here's our equivalence point 7, right? Right about here or whatever.
Also the volume of the NaOH for the equivalence point, which will
yes.
Our liters that we need.
We need the volume off of here at the equivalence point, because that's how much of the titrant was added to get there. So this is going to be pretty much directly in the middle, so that's going to be 25 milliliters, right? Because the scale is by 10, so I can estimate to the ones. That's pretty much all I can do there. So change this over to liters, 0.025 liters. Then we can do the stoichiometry. Now, I'm not going to rewrite the balanced equation for this one because we just used hydrochloric and sodium hydroxide. Oh, this is hydrochloric and sodium hydroxide. So we know it's 1 to 1 to 1 from the previous question, so you already have the balanced equation for it. Start with your liters. 1 liter, use the molarity as a conversion factor. Moles. Okay. Then we can do 1 mole NaOH, 1 mole HCl. That's going to give us the moles of our hydrochloric acid that were in the flask. Which is 0.01125 moles. Then all we have to do, remember our molarity equation, divide by the liters of the analyte. There were 20 milliliters added to the flask, so let's change that over to liters. 1, 2, 3, right? Divide this by, like so. 1 more 0. And now we get the concentration. And looking here, because the graph only gave us 2, technically this should only have 2. So I'm going to go with 0.56 molar HCl. I think I put it as 3 on the next slide, but technically I should have realized that the graph only has 2, so I should have gone off of that measured value. Now we kind of already did B, because we marked the equivalence point here, as X marks the spot on there. Now, drawing a circle on the curve where the HCl is in excess. Yes?
Since the HCl is more acidic, we know that when there's excess HCl, the solution is going to be more acidic. Right?
Yes, so which side of our S do we want there?
The left side.
We want the left side where the pH is lower. We want down here because pH, you know, has to be what? Below 7 to be acidic. 7 is neutral, above 7 is basic. So the part where it's in excess is going to be at the lower pHs. The inflection point is when it's equal, of course, the moles are equal, and then if you go above the equivalence point, past the equivalence point, now the sodium hydroxide would be in excess. So this is what we got so far. Oops, never mind. I'm just going to erase over here on the graph then. Let's go back. Because for the next part here, it says, on the graph, sketch a curve showing what the titration would look like if 10 milliliters of the same HCl sample were used. Yes?
So we know that it's going to start at the same 0, however, it's going to be steeper because if we're adding the same amount of reactant to a same amount of titrate, less analyte, then it's going to have a greater effect on the pH.
Okay. Technically, it's really not going to change the pHs of the beginning or the end point. But if we're only using 10 milliliters of our titrant instead of 20, what does that do to the moles of the acid? It cuts it in half, right? If we're using half of the volume, then we also have half of those moles. So if we have half of the moles, how much base are we going to need to neutralize it? Half of what the base was originally added. So if we added 25 milliliters, how much base do we need to get to the equivalence point? Only 12.5, right? So if you're drawing this on here, your curve is still going to start down here about the same pH. The difference is our equivalence point is going to be around 12.5. So this is where I would make a dot here. So it's still going to start off like that, but it's going to go up sooner and then round over like the other one.
So it is like sort of kind of.
It's not steeper, it's just you have less.
It's like it's going. I'm sorry, I'm articulating badly. Never mind.
I wouldn't say the steepness of the grass change. It just shifts over to the left. So you have less in this particular area before it gets to the inflection point. But it is the same shape, and I did kind of draw this a little bit higher. It should curve over just like the other one and be like in line with the other one. The only difference is you only had to add 12.5 milliliters because we cut the moles of the acid in half. That means you have to add half of what you did for the base to get to that equivalence point. And that's what I try to explain down here on this next part. Why are we not advancing? Oh, I see. Hold on one second. Forgot to hook this back in. Apparently my battery's dying. Okay, so now it should work. So the graph is the same shape, but the inflection point at about 12.5 instead of 25. Because the moles are cut in half for the acid, so you need half of the moles of the base. So half of the volume of the base would be added. Like so. And I'll draw it again over here so it's a little bit better. So right around here, I would still put it right around 7. Just draw it, go up and over. Like so. Shifting the graph to the left. All right, this is a good one too. A new variation on a titration type problem. Aqueous solution made by dissolving 0.543 grams of an unknown monoprotic acid in 25 milliliters of water in an Erlenmeyer flask. Those are the triangular shaped flasks. After an acid-base indicator was added, 41.21 milliliters of 0.150 molar sodium hydroxide was used to reach the endpoint. Find the molar mass of the acid. First things first, everybody know what a monoprotic acid is. 1 proton, 1 H. So if I were to say it was a diprotic acid, that would mean it has 2 H's, like sulfuric acid is diprotic. And if it was triprotic, it would have 3 H's in the formula. So in general, the way you could write a balanced reaction for this is simply using generic HA plus the sodium hydroxide. That's still going to give you the water, because remember you get OH plus H giving you the water. But the other component is going to be some salt with sodium. Although sodium's going to spectate, doesn't matter. We don't need to care about that. So that still means that the mole ratio is going to be 1 to 1 to 1, right? If it's monoprotic, it's going to be 1 to 1 to 1 mole ratio. Now, the other thing we have to contend with is molar mass. What is molar mass again? Molar mass is, what's the equation for finding molar mass?
Grams times moles.
Remember, molar mass is grams per mole, right? So mass over moles. That equation is from a long time ago and back in our very first set of notes, Unit 1. Guess what they gave us in the equation? They gave us the grams of our unknown monoprotic acid. What do we need to figure out? The number of moles, and we can do that by doing the stoichiometry of the titration. So, let's do that. 1, 2, 3, change that to liters. Start with your liters of your titrant. Work it to the moles of the analyte. 0.04121 liters. 1 liter equals 0.150 moles NaOH, and 1 mole NaOH is going to be equivalent to 1 mole of our monoprotic acid. So now we can find the moles of the monoprotic acid. And I'm getting 0.00611518, whatever. You can go to 3, you can keep it in, it really doesn't matter. But this is the moles of our monoprotic acid. So now we can plug it in and find molar mass. 0.543 grams over 0.00618 moles. What are we going to get for our molar mass? Getting 87.9 grams per mole. looking at our data table, which one do we think it is? The one that matches the closest here, 88.11, happens to be butyric acid. And check, it is monoprotic, so that's good. And they could have this as part of an extended FRQ, and then they could ask you a solubility question later because there's solubility data in here too. So butyric would be our monoprotic acid. Okay, almost done. Let's talk some redox. Read all about it. Redox titrations are very similar to acid-base titration. Slight change of a few things. Color change is produced when an oxidation state of a metal ion in the reaction changes. Because a lot of our ions for redox, they change colors with different oxidation states. Or potassium permanganate is a self-indicator, where the solution shows a light pink purple color when the endpoint has reached. We're going to be using potassium permanganate in our titration that we're doing on Friday. As you can see, it's pretty much a dark purple, pink color. Now, when you add this to your solution, you really need to stop when it just starts to flash and linger at a light pink. If you keep adding and it gets dark like this, then you've gone past your equivalence point. But you'll add just enough so that that pink color lingers, a light pink color lingers. Potassium permanganate is one that, or permanganate is a strong oxidizer, so it's used a lot in redox titrations. Now, typical redox titration problem. Sometimes they give you extraneous material that you don't really need to read. Sometimes they add in a few extra things. So, like potassium dichromate is used to titrate a sample containing an unknown percentage of iron. So we have some unknown like metal sample that has iron in it. It could be like iron ore that they dug out of the ground or something. The sample is dissolved in acid, phosphoric and sulfuric mixture, basically to change the iron from its atomic form, its elemental form, into iron 2 ions. Because when it sits in solution as iron 2 ions, you can react it and figure out how much iron was in the original sample. So the solution is then titrated by potassium dichromate, producing iron and chromium ions in acidic solution. Titration requires 32.26 milliliters of potassium dichromate for this particular sample, 1.2765 grams of that original sample that they had iron in it. So determine the percent of iron in the sample and then figure out which sample was reacted with the acid. We're going to do two things here. First, we're going to figure out the percent that's in the iron in the sample. Percent of iron in the sample. Okay? So, we start with our titrant, because that's the stuff we know. Titrant right here, molarity, and our volume. So we change this over, 1, 2, 3, change that to liters. 0.03226 liters. 1 liter, the molarity of our titrant. And this is K2Cr2O7. Now, in the balanced equation, you can see that they took out the spectator, potassium, and they only went with net ionic there. They only have dichromate in here by itself. So we're going to change it over to dichromate. So 1 mole K2Cr2O7 has how many moles of dichromate? Only 1. Good. So go from the entire compound to just the dichromate ion. Once we get there, then we can now do mole ratio. So moles of the dichromate to moles of the iron. And we look at our balance equation. There are 6 for the iron. There is 1 for the dichromate. And now, one other last little step, because our sample is in grams, so we shouldn't stop at moles. We should continue on and go to grams, so we can figure out the percent at the end. So 1 mole of iron is going to have 55.85 grams of iron. Then we calculate this, and we figure out how much is iron from the titration. And it's not a large amount, so we get 0.7 or 17557. This one has 4, this one has 4, so I'm going to go 4. That's how many grams are iron. Now, to find the percent of iron out of the entire sample, all we have to do is what? Part divided by the whole times 100. So what do we get for our percentage of iron? And yes, 13.76% sounds correct. Well, that's part A. Now we have to figure out which substance it is. So part B, we have to figure out if it's iron 2 phosphate, iron 2 iodate, or iron 2 acetate. All right, so basically you have to do a bunch of percent comps here. So in this particular compound, we have 1 iron, right? 55.85 over the total. Now we have to figure out the molar mass of that. 55.85 plus 4 carbons at 12.01 plus 6 hydrogens, 1.01, plus 4 oxygens at 16. So this is out of the entire compound times 100. Well, that doesn't look like it's going to be 13% to me, but here, let's go ahead and just calculate it. I'm getting 32.11%. So that's not it. Let's go ahead and do this one. Now there are 3 irons here, so I have to do 55.85 times 3 first. So this is my top number. Over the whole thing, so add in the phosphoruses, there's 2 of them, 30.97. And add in 8 oxygens at 16. This is 357.49 times 100, and that is definitely not going to be 13%, but we will figure it out just for fun. Getting 46.87%, something like that. So it's not that one. So it must be this one, but let's just check it just in case. 55.85 over the total plus iodine. Iodine is 126.91, it says. 126.91. 0.91 times 2, and 6 oxygens at 16. I'm getting 405.67, something like that. And we will see that this one probably is going to be our winner. So like 13.77% or whatever. This is the winner. That was what was in our sample. So maybe somebody found these, tested them, knew they had iron in them, didn't know what else, able to figure out the percentage. One last little redox titration to try. I'm gonna have you go ahead and see if you can set this up. Pulling antimony out of stibnite. Okay. So see if you can figure out the percent of the antimony in the stibnite ore. Okay, so here you want to start with the titrant, which happens to be potassium bromate. So that means you're focused on the bromate in the reaction. Remember, potassium is going to be a spectator because it's going to stay soluble. So it's going to be pretty much factored out of the reaction. So move it over 1, 2, 3, change it to liters, start your track. Okay, we have 1 liter to 0.250 moles, KBrO3. 1 mole KBrO3 is going to be equivalent to 1 mole of bromate. And then 1 mole of the bromate is equivalent to how many moles of the antimony? 3 moles of our antimony. And then because our sample, once again, is out of grams, we're going to go ahead and continue on and change it to grams. So 1 mole of our antimony to, isn't it, 121.76, I think on our actual periodic tables, that's what it says. It really probably won't matter. I get 1.995 grams of antimony. Now, in order to find the percent, you would do 1.995 over the sample, 9.62 times 100, and I believe you get 20.7%. Like so. Now, there are a couple more practices in here, and I do suggest you try to do them. What you can do here is work the problem. You'll notice in the PowerPoint, you can pull it up from Schoology. I put in the solution of how to do it, like so. This one involves actually reading the burette. Remember, the burette reads backwards. It's like an inverted scale. And here is the info that you need for the answer. You can check your answer. And last but not least, the third practice is a redox titration here. Welcome to try it. And this one starts out as a gram sample of the sodium oxalate, so that's kind of awesome. So you start with the grams, you can work it to the moles, and eventually figure out the potassium permanganate. So definitely attempt those, see if you can do them. There's also a few more in your problem set for you to practice the titrations, the acid base, and the redox.